Okay, let's roll. Ready.
Okay, do I need to put this on or no?
Yeah, just throw on the lab. It's a wireless, so it should be easy.
Okay. Okay, well, hello everybody. My name is Ajay Agrawal. I'm a professor of applied economics at the Robin School. And my good friend Steve here asked me to come and give you a presentation on some of the things that we're thinking about with regards to applications of machine intelligence and related to Mersivity.
Mersivity.
Right here.
Yeah.
And so effectively thinking about how machine intelligence is, it's evolving so quickly, how this can be related to the things we care about with regards to people on the planet. Okay, so I'm going to make 3 points. The first one here, people here probably know this already, but that AI is, in its current incarnation, is effectively just computational statistics that does prediction. And but what's, I think, attracted so much attention recently is how powerful prediction can be, and how many things we can do with prediction. So the myth here is that AI is a magical technology that can do almost anything, but in essence, especially the current incarnation, that is applied machine learning, is effectively computational statistics that does prediction. But I think where things have evolved quite quickly is obviously in the power of these multimodal statistical tools and the extent to which we've been able to frame such a wide range of problems as prediction problems. So in our economic setting, we characterize prediction as taking information you have to generate information that you don't have. And so that includes all the things that, for example, in a place like the business school, everyone's familiar with prediction as in spreadsheets full of data, for example, of historical sales data, and the thing that you want to predict is sales in Q3 next year. So the data we have is historical sales data. The thing we don't have that we want to predict is sales in the future. But then once we started to recognize that other applications would be like data we have are pixels in a medical image, and data that we don't have is the label on a tumor as malignant or benign, that's also a prediction problem. Effectively, the classification is a prediction problem. That we started recognizing that means we can build machines that can see. And so I think what's most interesting that's happened in the last 5 to 10 years in machine intelligence is we've recast a lot of problems that we didn't used to think of as prediction problems into prediction. And so people here are very familiar with these types of problems in some other settings. It's a surprise to many people that, for example, the way we're solving machine translation today is via prediction. And the way that we're solving this one here on the far right, the particle distribution size, this is a mining application. So up until quite recently, a thing that they care about in mining processes is what's called fragmentation index. So just the degree of fragmentation of the material right from the initial blast all the way through the process. And so, for example, they would often stop the conveyor belt, and a human would come along and measure how many big rocks, medium-sized rocks, small rocks, and sand is, and then calculate the fragmentation index in order to make adjustments to the crusher. And now they don't stop the belt; they just have a camera that sits on top, and algorithms that identify edges of rocks and enable the measurement and calculation of the fragmentation index, and so on. All these other applications problems that we've solved by converting them into prediction. And then, of course, along came language. So people have been working in natural language processing, of course, for a long time. But I think even experts in the field were surprised with the performance of these recent language models. And obviously the most common one, or popularized one, is OpenAI's ChatGPT. And so, this is a question that I asked ChatGPT about Mersivity, and asked the question, what will be the greatest challenge with respect to achieving this? And its response was not an unreasonable response in terms of the greatest challenge being collaboration and ethical frameworks. And it raises the question that I'm going to lean into here, which is the thing I've circled, or put the box around, which is ensuring that the technology respects individual rights, is unbiased, and aligns with societal values. Aligning with societal values is the one I'm going to drive towards in terms of caring for people and planet. I'd like to just think for a moment about the timing of these things. So many of you are probably aware that OpenAI, the chief scientist there, is a former student here at Ilya Sutskever, that Elon recruited to be chief scientist at OpenAI. And he sent us around this initial model, the first GPT in 2018, to play with. The vertical axis here is the number of parameters in the model, so you can think about this as the size of the model and the amount of compute required to train it. Then sent the second model around for people to play with in 2019. And then there was this investment, significant investment for a startup, $1 billion in the middle of 2019. And then they took that investment and effectively invested entirely almost entirely into compute. And so they did this. And so that was the first model, second model, and then the third model. And the reason we just wanted to point this out was just to give a sense of the speed with which this is accelerating. Everybody here probably is well aware of that, but just important to note. So as we're thinking about how we adapt these intelligent systems to things that we care about with regards to people and places and the environment, that there's some sense of urgency because things are moving quite quickly. Okay, and then just to finish this first point, these language models are LLMs, large language models, focused effectively on prediction, what they're doing is predicting sequences of tokens. So you can think of them as token sequence prediction machines. And so that's think of it as they're predicting, next word. What's on the horizon that I think is very important to have in our crosshairs as we're thinking about Mersivity is how these intelligent agents are moving from the digital world into the physical world. So while the language models are entirely living in the digital world, the technique is being brought into the physical world through a variety of channels, one of which are these LBMs, large behavioral models. So the large behavioral models are similar in their style to the language models. I'll explain how in just a second, but I wanted to begin by just pointing out that they're following a similar curve. So this particular one is Toyota Research Institute, that they have trained these robots on, at the time the article was written about September, October, on 60 skills. And their goal was 100 skills by the end of 2023. And then thousands of skills by the end of 2024. So it's on a similar, rapid growth curve that similar to the one I just showed you with language. Okay, but here's how we think about it. The people that are working on these behavioral models is that if you think about tasks, like all the things that we do, think about, for example, in terms of work. Just at the University of Toronto, all the different jobs people have, and if you took everyone's jobs and wrote down for each job the tasks that they do, that just on this campus there would be hundreds of thousands of different tasks, maybe millions of tasks. And so if you think about, okay, how would you train a robot to do all those millions of tasks? That seems like a very big job. But then if you step back and say, okay, let's say in the case of language, that every story you've read, every poem, every scripture is all just a resequencing of the same 30 characters, roughly 30 characters, letters and a few punctuation marks. And everything is just everything that's ever been written in English is a resequencing of those very small number of characters. That we can take these tasks and break down every task into verbs and nouns. And while there might be millions of different tasks, there is a much smaller number of verbs and nouns. And so the way we think about these behavioral models is that they are, just like the language models are predicting sequences of tokens, the behavioral models are predicting sequences of verbs or verb-noun pairs. So that if you give let's say a robot an instruction, like, can you please unpack the boxes and put the tools on the shelf, that it receives the instruction, and then its job is to predict what is the series of verbs and nouns that will enable me to most efficiently complete the task. So you can think of it very similarly to a language model. It's predicting sequences here. And so this is what I'm on the board of this company. It's called Sanctuary. It's Canadian, and they're building humanoid robots. And then so are others. I probably the most advanced right now is Tesla. And so Tesla's also building humanoids. And a thing that it feels like, even though Elon says this, it doesn't seem like it's really, the penny's dropped yet. So this is something he said at the last shareholder meeting, is that everyone thinks of Tesla as a car company, and he's basically saying Tesla's not a car company; it's a humanoid robot company. These humanoids, once they are trained with this kind of general level intelligence, this will be a much more valuable part of their company than the cars. And that the economics of these are such that labor wages are going up, but the cost of all the components to make these types of general purpose robots, so general in their capabilities. So for example, humanoid form is general, and with general intelligence, that all the cameras, the servos, the actuators, the cost of all those things are falling. And so just as a kind of put a finer point on this, about 3 or 4 weeks ago, China announced that this was now going to become a top priority for them, and as a result, the stock prices of the component makers went up, and all the things. Okay, so these are things happening in this field of machine intelligence. The problem here is, are we racing towards building AI systems that are powerful? Are these designed to benefit all people and the planet? And how would we think about that? So obviously, these are just a few examples of the types of concerns people have. There's many different types of concerns. But I'm going to draw where I think our focus can be very usefully applied here, so that we're not caught off guard, is thinking about how these types of systems evolve. And so a lot of people compare artificial intelligence to electricity. they say AI is going to be ubiquitous in the way that electricity is. So lots of different organizations making this comparison. So I wanted to point out a couple things about electricity and lessons we can learn from electricity. That electricity invented in the late 1800s, and after 20 years of having electricity available, still less than 3% of U.S. factories were using electricity. And so, the basic sales pitch at that time for electricity was that it would save you input costs. So, for example, if you were lighting up your factory with oil lamps, then you say, look, you can operate a little more cheaply if you use electricity. But you can imagine that existing factory owners did not want to tear apart their existing infrastructure so that they could implement electricity. Too expensive. So the only ones who were trying it were people building new factories. And even most of them said, no, I'm going to stick with what, we're going to stick with what we know. So only a few entrepreneurial factory owners who are building new factories said, okay, I'm going to try that. I'm going to try electricity. And they're the ones that are showing up here. Entrepreneurs building new factories and trying out electricity. And here's what happened. This is a quick sort of stylized history of this. Is that, this is, you can think of this as a reasonably representative picture of what factory would look like at this time. And I just want to draw your attention to the top left corner. So there'd be some source of power outside the factory, like a water wheel or a steam or something, and it's turning that steel shaft. And the steel shaft in that top left corner there, this steel shaft is turning the wheels are pulling the pulleys are powering the machines. So when the first few entrepreneurs were experimenting with electricity, they didn't need the steel shafts anymore, because now instead of having those steel shafts turning and pulling the pulleys and so on, they would have an electric cable coming into the machines, powering a motor, and the motor would be turning the machine. So as they were building these, the designers said, wait a minute, there's these big, thick timber columns that they were using to support those steel shafts, because the steel shafts were so heavy. They needed these big, thick support columns. Now that they didn't have the steel shafts, they said, why are we still building our factories with these big, thick columns? We don't need those anymore. And so they realized they could have much lighter weight construction. So in addition to any savings they got from the electricity, they could now build lighter weight construction factories. And so that became an additional benefit. Then the second thing that happened is you can see that those thick timber columns that were used as supports are spaced about every 8 feet in order to support the steel shaft. And so the problem was that everywhere that the column was supporting the steel shaft, you can imagine the steel shaft is losing energy due to friction where it's being supported. And as a result, the steel shafts could only be a certain length. If they were any longer and they needed more supports, they would lose all their energy due to friction. And the thing would just stop turning. So that meant that the factory could only be a certain width. And that's why they would build the factories vertically, so they had multi-story factories. After they started removing these columns, they said, why are we still building vertical factories? It's much cheaper and more efficient if we build single-story factories. We're not limited by length anymore because we're not using the steel shafts. So now they moved from multi-level vertical factories to single-story factories. So now we've got single-story, lightweight construction. Land was cheap, so these became much cheaper to build, these factories. And that's a benefit above and beyond any savings from electricity. Then the last thing that happened is that as they're building more and more of these factories, the designers keep realizing that they can do new things now that they're unencumbered without having those steel shafts. They said, now that we've got these long single-story factories, we can redesign the workflow. So how we organize the people and the machines and the materials. And some of these factories got a 500 or 600% productivity boost from just reorganizing their workflow now that they had everything on a single story. And then lastly, the machinery in these days would break down a lot, and you don't even need to have an engineering background to figure out what happens when one of these machines breaks. When one of these machines goes down, the whole factory stops. Just as you can see, they're all connected. So once they replaced all this, where such that every machine had its own power cord and motor, one machine would break, the rest of the factory could keep on going. So the economics of these factories changed substantively. And the key here was that it was not just electrifying the factory. Electrifying the factory enabled a total system redesign. And that's going to be like my central point here with regards to Mersivity, is that as we introduce machine intelligence into our systems, we don't have to keep our systems the way they are and just give them these predictive capabilities. We can rethink and redesign from scratch how we build our infrastructure. So what I showed here in the very left, that was the actual adoption pattern. If that had just continued on as it was going, it would look like that pink line. But instead what happened is, as people started to realize the benefits from electricity were way more than just saving on the lower fuel costs for oil lamps, for example, then instead the adoption rate was this. And that seems to be the curve that it feels like we've started to go on with machine intelligence, that as people started to realize the power of these computational statistics, that a lot of capital now is flowing into this, and the curve is starting to shift upwards. This is our moment for rethinking how we interact with other people and the planet. And this is happening in real time as we speak. This just came out a few weeks ago from President Biden's office, and this is an executive order of how the U.S. government is going to handle using AI just within the government. So this isn't their regulations telling other people how they're going to use it. It's just saying within all the federal agencies how they're going to use AI. And so they start by saying AI, one of the most powerful technologies of our time, that we must use it, and we also must manage its risks. And just to give a sense of the time, they have a sentence like this, which is, within the next 60 days, every federal agency has to appoint a chief AI officer. Now, who knows what that's going to actually, result in? But the point is, a government doing anything in 60 days is fast. And so I just wanted to kind of convey a sense of how these things are moving. Okay, so I said I'd make 3 points. Here's my final point, which is, how do we embed humanity into these AI systems? Along the lines of the theme of this meeting on Mersivity. And how do we embed it even when there's no explicit human in the loop? So obviously one way to do it is having humans in the loop. But what about systems that we want to fully automate and yet still preserve humanity into the process? So anytime we make a decision, any decision, a big decision like which house to buy, or a small decision like when you walked into this room, which chair to sit in. Any decision we make has two components. We often don't think of them explicitly, but they're there. Prediction and judgment. So anytime we make a decision, we have prediction and judgment as an input. And what AI is enabling is decoupling these two things. So effectively, we're handing the prediction job, the computation to the machine, and the human is doing the judgment. And as we decouple these things, you can think of this as very similar to the factory example I showed, where the factory example, what electricity ended up doing was it decoupled the power source from the machine. And when you decouple the power source from the machine, it opened up opportunities for redesigning the whole system. Okay, so let me just give you a little more detail what I mean by prediction and judgment. So this is about half a century's worth of research in decision sciences. And a key idea you can take away here is that so decision theory is a branch of applied probability theory concerned with the theory of making decisions based on two things. One is assigning probabilities to various factors. That's the prediction part. Okay, assigning probabilities to various factors. And the other is assigning numerical consequences to the outcome. That's what we refer to as judgment. And so when we get into Mersivity and we're talking about how do we link together what we're doing in the machine, what Steve refers to as the bits, with the things, the atoms and the genes. In my view, the way we're going to do that is through this last part of this decision theory, which is how we assign numerical consequences to outcomes. That's judgment. And our judgment is going to reflect how we care about each other, other people, other animals, and the planet. So I'll illustrate this with just a simple example. And so this is, try and think of an example as the simplest of all decisions. So imagine that you're about to head home today, and you're deciding whether to pick up an umbrella on your way out. And so you look outside, say it's a 20-minute walk home, and there's a 25% chance of rain. Or you can imagine you're at home and you're about to walk here to the university. And so you're at home and you're deciding whether to grab an umbrella as you walk out the door. So imagine that you're coming here, 20-minute walk, there's a 25% chance of rain. Who would bring an umbrella? Just show of hands. 1, 2, 3. Okay, 4 people. So 4 people would bring an umbrella. And this is going to be actually quite important. So so the decision here is to take an umbrella or not. And if you take an umbrella, no matter what happens, whether it rains or not, you're going to be dry because you've got an umbrella. If you leave the umbrella, then on the plus side, you don't have to schlep around an umbrella. On the downside, if it rains, you're going to get wet. Okay. So there's uncertainty. And anytime when we're talking about prediction, the sort of the other side, the flip side of the coin of prediction is uncertainty. So the uncertainty here is we don't know if it's going to rain or not. Then there's an outcome. And the outcome is we're either going to be dry or wet. If we take the umbrella, it doesn't matter what happens, we'll be dry. If we leave the umbrella, and if it rains, then we'll be wet. Okay, so the prediction part here is just the prediction of what's the probability it's going to rain. And so in our example, we said 25%. Now here's what's interesting. Everybody in this room had the same fact set. Everyone had the same facts, which is you're at home, you look out the window, 25% chance of rain, you're going to do a 20-minute walk to come here. Would you take an umbrella? So everyone had the same fact set, but different people made different decisions. Some people said yes. In this group, 4 people said yes, they're going to take an umbrella, and other people said no. So even though everyone had the same facts, and they knew the same probability, they had different preferences, and that is judgment. So just as an aside, many people probably saw this, but I just added it since it's pretty recent. November 14. This is from Nature. Yet one more instance of AI generating a clever prediction, in this case for weather. Okay, but I want to draw your attention to the blue numbers here, because this is in my view, the key of injecting humanity into machine intelligence. Which are in economics we call these the payoffs. So imagine here that if you take the umbrella, then it doesn't matter if it rains or sunny, because either way you're dry. And so imagine you have a payoff of 100. And then if you leave the umbrella, and if it rains, then you get wet. Now, some people said, if I get wet, that's a really bad outcome, and therefore I don't want to take that chance, so I'm going to take the umbrella. Okay, so the four people in this room who put up their hand, they had a higher number in a more negative number. So for them, let's say it was minus 400 or minus 500. Whereas for other people who said, I'm not going to take an umbrella, they had a low number. They didn't care that much if they got wet. So to them, it was not a meaningful. I know for Steve, he probably wouldn't care because he's swimming in Lake Ontario all the time. So this is where we put our values, our preferences. And then we simply take the probabilities and multiply them times the outcomes. And so and that thing in the green is what we call the expected payoff. So this is just the probability of going down that branch times the payoff of being on that branch. And so here you can see that the payoff is higher for leaving the umbrella than taking the umbrella. So these blue payoffs are more representative of the people who did not put up their hand. The people who did put up their hand, they would have had different values in the blue column. Everyone here had the same pink because we all face the same probability. And so these payoffs, what we call judgment, is like, where do they come from? And so when we are making autonomous machines, the values that we put in these blue is where we imbue the machines with our judgment. And so, for example, if you've been playing around on the language models, the fine tuning that resulted in ChatGPT answering questions in the way that it does is because that mechanism of reinforcement learning with human feedback, fine tuning these language models, is a technique for imbuing the language models with judgment. And in this case, it's the judgment of a bunch of people that live in Northern California, and they've decided that the language models should answer questions in the way that they do. And so when I showed you that, for example, the humanoid robots and those behavioral models, same thing. We will be imbuing those behavioral models with our own judgments. And they will reflect how much we care about nature, how much we care about animals, how much we care about, for example, access to the lake that we were just talking about. Every time there's a decision, how do machines make those decisions? If we have given these intelligent systems so-called decision-making rights, remember, the machines just do predictions. The only way that they can turn the prediction into an action is if we have also given them judgment. So by taking an action, it reflects that they have been given judgment. And that judgment comes from people. Machines have no judgment. We've made a lot of progress in machines being increasingly sophisticated with respect to their ability to use multimodal data to make predictions, but zero progress in machines having judgment. Judgments come from people. Okay, so just as a sort of a simple way to think about the world and decision making, this is where. So if we were to build an AI, a machine, instead of just doing like the Google AI I showed you that does the weather prediction, let's instead imagine we wanted to build an AI, a robot that was an umbrella dispenser, so that as you're walking out the door, the robot either just hands you the umbrella or says, no, you don't need the umbrella today. For the robot to do that, it has had to learn your judgment. So it has to have enough data to be able to predict what your preferences are in order to make the autonomous umbrella machine, which is different than the AI that just does the weather prediction. Because that robot would have to know that 4 people sitting in this room wanted the umbrella when the weather was 25% chance of rain, and the rest of the people didn't. Okay, so a puzzle here that I find as useful, just to kind of get your mind around thinking about how is prediction going to change systems and change the way we design our systems, our infrastructure, and everywhere that we put machine intelligence into our infrastructure. This is just a useful thing. So like, if you think about where is the one place in every city where middle income people get offered all kinds of luxury goods and ultra high net worth people don't? Anyone want to take a guess? Yep.
The physical urban core of a city?
It's related to the urban core. It's related to the urban core.
Balls.
The answer is actually airports.
Oh.
And the reason at airports is because when you and I go to the airport, like at Pearson or something, we are presented with all kinds of goodies. But if you're ultra high net worth, this is not what you see. If you're ultra high net worth, then you see this other terminal. Because if you're ultra high net worth, you fly private. And if you fly private, how it works is you drive up in your car, you get to the airport, you open the car door, you step out, you pick up your bag, and you walk right through this terminal because there's nothing there. And go right through the terminal, onto the tarmac, and onto your plane. And the reason there's no Gucci or Prada in a terminal for people that fly private is because you don't have to wait. There's no waiting. Airports are a monument to uncertainty. But the reason that we have to arrive so early to the airport is because of uncertainty. And because we have to arrive early, we have to wait. And because we have to wait, they've got people captive and they sell them stuff. If you had a sufficiently high fidelity prediction that you knew exactly when you could walk out of your front door and then go right to the airport and not have to wait and onto your plane, like a person who flies private, there would be no Gucci or Prada at the airport. My point here is that nobody goes to the airport because they want to shop for luxury goods. The airport has been designed like almost everything, has been designed to provide ways of managing uncertainty, and we're so used to that we've forgotten why that infrastructure is there. So in other words, you can think of every organization has been optimized for a pre-prediction world. So it doesn't matter what it is. Everything, and sometimes there are rules. I was just talking to somebody who works for a company that makes airplanes, and they have a preventative maintenance system where every 100 hours they just replace a particular part. That's a rule. A rule is after every 100 hours, just replace the part, even if the part is going to function for another 100 hours, because they don't know, because of the uncertainty, they handle that with a rule, and the rule is just replace it after 100 hours.
That's called group replacement. They do it with light bulbs. When there's
With
a
light
big
bulbs.
scaffold and it's hard to get up there, they change all the bulbs.
All the bulbs at once. But if you had a high fidelity prediction and you could look at that piece of machinery and say, this is still good to go, and that every day or every hour you could predict what's the likelihood of failure, then you could move away from the rule of just every 100 hours and replace it when it crosses some threshold. Let's say any time that it exceeds more than 0.1% chance of failure, change the part. So the point here is that every organization is riddled with scaffolding that's designed to manage uncertainty. Sometimes it's rules, sometimes it's insurance, sometimes it's redundancy, whatever it is. We've built this infrastructure to deal with uncertainty, and now, in many cases, we've forgotten why it's there. Just like if I ask, why do we have Gucci and Prada in the airport, people have forgotten that the reason it's there is because of uncertainty. That if we didn't have the uncertainty of the airport, we wouldn't have all that stuff. And a lot of this scaffolding is invisible. So now is our opportunity, as we are introducing machine intelligence into all kinds of things, that we can re-optimize our systems for a post-high fidelity prediction world. And that is I think, an opportunity to bring in these principles from Mersivity in terms of rethinking how we interact with nature, with animals, with our environment. This is our moment to do that. And my last point here is that, there's something that's interesting about machine intelligence, is that it's the first tool in history that we built that learns from use. There's never been another tool that, as you use it, it learns and becomes increasingly powerful. And so we get more data. As we get more data, we can make better predictions. We make better predictions, more people use it. And when more people use it, we get more data. And so we get this loop. So, for example, different people use different search engines. How many people predominantly here use Google? Most people that use predominantly Bing? One person? Usually in a room like this, there might be 2 or 3 people that use Bing. It's very hard for especially before ChatGPT, it's hard for anyone to catch up to Google. And the reason is, of course, because every time we use Google, we are further training their model. You type in your query and you hit enter, and Google makes a prediction, takes your character string, makes a prediction, what are the sites most likely you want to see, and then it shows us 10. How many people regularly use I Feel Lucky? Almost nobody. If we all used I Feel Lucky, the course of history would have changed. Because if you use I Feel Lucky, then Google automatically just opens up the website of whatever would have been the first link. But remarkably, almost none of us use I Feel Lucky. And instead, we choose to do work. Now, usually we choose the thing that's most convenient. But in this case, we choose to do work. So rather than hitting I Feel Lucky and it just opens up the top link, we don't. And therefore, we get 10 links. And then we use our monkey brains and we read them all. And after we've read 10, we click on one. And so let's say we click on the 4th link. Google says, oops, we made a mistake. We thought that was the 4th best, but you just clicked and told us it's the 1st best. It updates its model. So every time we're using Google, we're updating them. So all of us that raised our hand, we all work for Google. We are constantly updating their search model. And that's what makes it so hard to catch up to Google, is that every time you use their search tool, you are improving. So this is my last slide. I don't know who's going to win the autonomous car race, but Tesla thinks maybe they'll win the race because they've got more vehicles on the road that are actually collecting driving data, all the sensor data. I don't know who's going to win it, but I've spent a fair amount of time in Washington over the last 7 or 8 years. That at some point one of these car companies is going to make it over the line, and they're going to pass all the regulatory requirements, and you'll be able to take your hands off the wheel. And in any city in the U.S. And when that happens, at least for the first few years, those cars are still going to ship with steering wheel, accelerator, brake. And so when you're in one of those autonomous cars and you tell your car, okay, I want to go here or there, and it starts to go. Anytime you touch anything, for whatever reason, car is driving along and you say, no, I want to turn left here, or no, I want to slow down, and you are giving it feedback data. And so now that car company will have hundreds of thousands of people driving their car in autonomous mode, giving them feedback and learning, updating the model. Then whatever, 6 or 12 or 24 months later, another car company will make it over the regulatory hurdle. And now there'll be another car company with vehicles on the road. But how many Americans are going to want to climb into a car and drive with the second best AI? The first one has been learning for 24 months of collecting data from users and getting better and better. And the marginal cost of software is 0. So just like Google, like people that don't want to use the second best search engine, it'll be hard to convince people to use the second best AI. And that's why when you know, sitting here in the engineering department and open up the paper and are reading about, you know, investments in Silicon Valley and places putting capital into machine intelligence projects, it's easy to wonder, like, why are they putting so much capital so fast? And it's because the prize is so big for being first, that it's a technology that lends itself to, if not natural monopolies, something close to that. So if we care about things like how these systems impact the environment, their implications for sustainability, for the planet, I think it's important that we put our values into the judgment that I was describing before reasonably quickly, because the systems are being developed quite fast, and it all seems to be accelerating at a reasonable pace. So with that, Steve, I'll wrap it up.
Okay, that was a very, very good talk. That was fantastic. Beautiful. Yeah, and there's, if you want to learn some more, read some of these books. Really, really eye-opening read there.